All right, we're back, and I wanted to talk a little bit about some graphical kind of information, tracking down where the graphs of particular equations, which will transition into talking about functions the more we do this calculus thing, of where the graph would happen to cross the coordinate axes in your standard XY coordinate plane. So um, because I like to get maximum mileage out of my examples, I'm using that same guy from before, the 2x squared minus 12x minus 14. Now, this is actually an equation. Normally the thing by itself I would have just called like an expression or something earlier. So we have y equals this guy. And our objective is to figure out where it crosses the vertical axis, the y-axis, and where it crosses the horizontal axis, the x-axis. So the first order of business, we want to find the y-intercept of this thing. That's generally the easier of the two to work with. And bear with me a bit because this can end up seeming kind of backwards. So if we want to figure out where we cross the y-axis, we set our x variable equal to 0. I know there's often a little bit of resistance, like, well, if it's the y-intercept, why not use y equals 0? Remember, we want to know where it crosses the y-axis. So if you imagine, like an xy plane here, all the points along that vertical axis, they have an x coordinate of 0. Thus, x equals 0. Now, I plug x equals 0 into this thing. I get y equals 2 times 0 squared minus 12 times 0 minus 14. And you're probably looking at me and saying, that's, why did you write out all this? I'm just being very careful. For what it's worth, if you had said, yeah, these two terms just completely go away, and all you get is negative 14, I'm good with that in general. So, all right, that's our y-intercept. That's the easier of the two. And hopefully this kind of makes sense. If the y-intercept required us to set x equal to 0, then if we want to find the x-intercepts, we set y equal to 0. I'm getting close to the bottom of the board and I'm kind of freaking myself out. So, all right. So now, this one's not quite as pretty. We've got 0 equals the quadratic equation right here. So, now, there's a couple of different ways you could do this. Again, your algebra background, some folks sort of reflexively go for our friend the quadratic formula. If you do that, that's perfectly fine with me. If you like to play around and try to figure out how something factors, also fine with me. But since I was kind of lazy and I used the same one from before, we already know how this thing splits apart, right? So it was 2x plus 2, x minus 7. That's not my cleanest 7, but it gets the point across. Now, in order for this factoring thing to work, we kind of need one key property of the way our real number system works. These two things multiply together, they give us 0. The only way that can happen, the only way you can multiply together two numbers and get 0 back, is if one of those two numbers were 0 in the first place. You could technically try, but don't. You've got cooler things to do with your time. So now we kind of take each of these guys separately, set them equal to 0. So we have 2x plus 2 equals 0, and then we'll have. And if you'd skipped over this part, that's kind of okay. If you would just jump to the punchline of giving me the x values, again, I get it. Because this one, we have to have x equals negative 1. I encourage you to go, make sure that you understand how to do the algebra, but I'm at the bottom of the board. I'm not writing over my son's Pokemon poster. So we have x equals negative 1. Over here, we have x equals positive 7. So this time around, we've got a pair of, distinct x-intercepts. It's not always the case. For most of the scenarios we're going to see over the course of this semester, you're generally only going to have one y-intercept, because if you're talking about something that is a function of x, so we'll talk more about functions later, but if you got something like this, there's only one place it's going to be able to cross the y-axis. We said I don't want to get too deeply into that because we're already on kind of a tight schedule here. So that's one example. I want to take a look at another one real quick where you do something a little bit different. Okay, it looks like I've upped the degree of difficulty a bit here because now instead of a quadratic polynomial, I've got a third degree polynomial or a cubic. But it's actually not that, I think it's easier, frankly. So we want to track down the x and y intercepts like we did previously. So as before, to find the y-intercept, we can set x equal to 0, and hopefully you don't need me to tell you plug 0 in here if you want to walk through it. That's fine. But so there's our y-intercept, y equals 0. You may sometimes need to report these as like coordinate pairs. So so if you were wanting to write it out, you could have 0, 0. I could have written out my x-intercepts from the last example the same way, but hopefully you get the idea. Context will generally tell you, if you were writing something by hand, I'm perfectly fine with you stopping at this point if a y-intercept is what we're after. All right, so now to find the x-intercepts, we set y equal to 0, and now this time around, it's like you could start trying to do like fancy factoring tricks, but it turns out there's not an awful lot of fancy factoring you need to do. Hopefully you notice both terms here, 9 and 3, they're both divisible by 3, so I can factor off 3. X cubed, x squared, they have a common x squared, so if I pull away 3x squared, I'm left with 3x from this first guy, minus 1 from the guy in the back. Do remember factoring away a 3x squared, it doesn't become 0, it's 3x minus 1. So now, same deal from before. These two things multiply together, we get 0. One of them has to be 0. So this guy here, the only value of x that would make 3x squared be 0 is, in fact, 0. So there's 1. Then we take this other guy, we set 3x minus 1 equal to 0 and solve. Go ahead, I'll wait. Sure. So you should end up getting an x value of 1/3 for your other x-intercept. So that's kind of it. Yeah, if you get down that sort of, opposite, like sort of cross 0 principle, I don't know what to call it. But, yeah, so to find the y-intercept, we set x equal to 0. To find the x-intercept, we set y equal to 0. I'm trying real hard to make sure I say that right, and I'm not 100% convinced I did it, correctly all the way through here. This is how I find my y-intercept. This is how I find my x-intercepts. So, before I call it, a video here, I've got one last thing I want to mention, but that kind of stuff, Okay, so I've got two last things I want to talk about here, kind of like in the Hall of Fame of classic algebraic errors that I'll end up stumbling across. And it comes back down to these, if you play around with exponents, it's kind of two examples of the same thing. But so I've got students, like I said, just about every semester, somebody at some point will slip and they'll be presented with something like x plus 1 quantity squared, and they tell me that it's x squared plus 1 squared, and then they'll drop the square from the 1 and tell me that it's x squared plus 1. Or they'll see a square root like this, and they'll break it into two separate pieces like this and say it's square root of x plus square root of 9, which is 3. Hopefully, you've already looked at what I've written and said, what is he doing? Because those are both catastrophically wrong. So I cannot emphasize that enough. Never ever do that. I know it's tempting because it's like if we had a 3 out front of this, we can distribute it across. But that's not how exponents work. That's not how roots work. Please don't do this. That will throw an awful lot of stuff off. So be careful with that. For what it's worth, in this instance, you could technically write like an x plus 1 times an x plus 1, so you've got 2 copies, and then you use the FOIL algorithm or however you want to multiply it out, and you get something. That's fine. There's not really much else you can do with it. You kind of just have to leave it as square root of x plus 9. So that's what I was wanting to say in this particular video. I do want to take a moment and address some stuff about functions and function notation, so that's what you'll see momentarily.